we'll see soon. There also. Oh, should I start? Sorry, I noticed now that the recording is starting. Okay, I'll continue from here, I guess, or maybe I don't know. So why we care about toric dynamical systems? Well, they are known to be locally stable and conjectured even to be that this equilibrium is globally asymptotically stable. We'll see more precisely more about this conjecture. And they also have exceptionally strong dynamical properties that I mentioned and will make more precise. But from the algebraic aspects, and we are also interested in this community on this side, first of all, the steady state set that I will define soon is a toric variety. So one reason that for their name, the toric dynamical system. So that's nice because the steady state set will be can be parametrized, so monomially parametrized. And then there is another reason, and we'll see soon why they're called toric. But let me mention that another advantage is that we can use tools from commutative algebra, computational algebraic geometry, real algebraic geometry, because here, since we deal with applications, we need to look at the real side to deduce properties and to grasp the dynamical behavior from these computations. So since they're so nice, this family of polynomial dynamical systems, toric dynamical systems, you might wonder whether they exist or whether we can find them easily. They're too nice to be true, or what happens. So here I have good news, or some good news, but also some bad news. I'll start with the good ones. The first good news is that there are some algebraic conditions on the parameters such that we can where we can plug in the parameters and see and check if the system is toric. So we can easily check if a given system is toric in this sense. And finally, I can say what's the second reason why why they are called toric, because of the fact that this set of parameters that satisfies the conditions these algebraic conditions is a toric variety. This was proven by Crăciun, Dickenstein, Schiu, and Sturmfels in 2009. And I plan maybe during the tutorial or during another lecture to look at this, to show you this proof, or at least the proof ideas, not today. So that's the second reason, because the first reason was that the steady state set is a toric variety, but now also this parameter, the set of parameters in the parameter space is a toric variety as well. Very good. These are the good news from the algebraic point of view. Now let's see what is the bad news. So the bad news is that in many cases, usually, not always, but in many cases, this toric locus, so the set of parameters that give rise to this nice dynamical behavior that I was mentioning before, that's very stable, is usually a set of Lebesgue measures 0 in the parameter space. So this makes toric dynamical systems quite rare, and we see this as a disadvantage for now. But here comes our contribution. The first result that I'm going to talk about, the contribution with my co-authors, Laura Brustenga, Imon Cuzi, and Gheorghe Crăciun. Well, we show that a system does not have to be toric in order to enjoy these nice dynamics. So a system can be disguised toric. And here is an inclusion. So the disguised toric dynamical systems enjoy all the nice properties of toric dynamical systems. So essentially, we extend the toric locus in the parameter space to the disguised toric locus. So to the parameter set that gives rise to disguised toric dynamical systems. And of course, I will make this more precise during the lectures, but now I want to give a big picture of what happens. So what happens, what's the advantage of the disguised toric locus? It usually is a positive Lebesgue measure set. So it's much, we gain much more information once we discover the disguised toric locus about the behavior of the dynamical systems coming from the network that we are looking at. What we leverage in our work is dynamically equivalent systems that was introduced by Crăciun, Jean, and you, at least in this context. And moreover, at the end, we give an algorithm that one can systematically apply. So if you have your favorite reaction network, you can apply this algorithm, these steps of the algorithm, and find the disguised toric locus. So this was the first part of the results that I want to talk during all the lectures. That's the plan. The second part, so still in this context, we knew already from previous works that there are globally stable systems that are not toric. But we were wondering now, since we extended this set of toric dynamical systems with the disguised toric, we were wondering if in some cases we can cover, or in general, if we can cover, here is a more detailed discussion about global attractor conjecture, but for now, just a simplified version, I want to mention that we were wondering if the disguised toric locus covers all the globally stable systems. So not just the locally stable, but globally stable. And I'll answer this question during my talk. We'll see if we manage or not, and if not, whether we find some globally stable system that is not disguised toric. That's the next part of the results. Still in this work with Brustenga, Crăciun, and myself. But I also plan in further lectures next week, as much as time permits, to look at some other results of mine with Hake, Satriano, and you, where we considered, so starting with the network, given a network, we consider invertible affine transformation of this network. So here is a sketch of such a case. And the question is, what happens with the disguised toric locus associated with the new network? And here is where I will mention this. I will give the answer. So, namely, the disguised toric locus is preserved. That's nice. So, it's preserved under invertible affine transformations of this of networks. So, this is very nice because you can compute the disguised toric locus for a simpler network, and then if you because sometimes the computations can be quite difficult, so it's very nice to have a way to deduce the disguised toric locus directly without redoing again computations from scratch. That's an advantage. And then, moreover, if time permits, I also want to mention some aspects or some properties, some topological properties of the toric locus. So before I was talking about the disguised toric locus, the one that is usually a positive Lebesgue measure set. But now, for the last part, I would also like to specify some properties of the toric locus in terms of the topological structure. Namely, we proved with Crăciun, Jean, in two preprints that I will show soon on a slide, so that if someone wants to read them, that the toric locus is connected, and moreover, we showed that it is a smoothly embedded submanifold of the Euclidean space. This is on the more topological side. Now I decided to mention. Sorry. Sorry. I decided to make a slide here with the references that appear during the talk and during the next lectures, in case someone would like to check. So this is number 2 here in the paper by Crăciun, Dickenstein, Shiu, and Sturmfels. This is the paper where they introduced this terminology of toric dynamical systems in 2009, and here you can see the proof of the fact that what we call now the toric locus is a toric variety indeed. So the parameter space, sorry, the parameters in the parameter space giving rise to nice dynamical behavior is indeed a toric variety. Of course, here I say a bit, maybe I don't get into details. Actually, we will look at this intersected with a positive orthant, because we deal with real algebraic geometry, real varieties, and Beatrice also mentioned this in her talk, but now I'm just giving, I don't go into details. Next, these are 3 and 4 will be the 2 preprints about the topological structure of the toric locus. And then paper here, the number 6 reference is the paper where we consider a fine equivalence of reaction networks and this preservation of the disguised toric locus with the Hake, Satriano, and you, my paper. And then in paper number 9, we can see the paper with Brustengai, Moncuzi, and Crăciun, where we introduced the notion of disguised toric dynamical systems. Number 10, in this paper by you and Crăciun, there are the basic, so who wants to start learning this very interesting subject, I recommend starting from reading also this paper, Mathematical Analysis of Chemical Reaction Systems. It is a review paper, and it's very nice to start. And then the fundamental paper was number 7, Horn and Jackson, where they talk about the general mass action kinetics, and I'll mention this later on. They consider they are very interested in the dynamical behavior, not so much on the algebraic side. Okay, so with this, I am ready to state a bit the overview of these lectures, at least of the next lecture and this one. So I start with some background on reaction networks, some terminology that we need, and already I know that some of these words and definitions were introduced yesterday by Betty. So I mentioned them quickly. However, I want to present them because they are maybe used in a different notation, and I think it's more coherent in this way. It's good to see them from different points of view. And then I'll mention in more detail what these properties I was saying before are. So from the dynamics, the algebra side of toric dynamical systems, I'll define the toric locus, and we'll see how an invariant that is called the deficiency of the network, which is a graph of the network, will tell us how far the toric locus is from covering the whole parameter space in terms of codimension, just to give an idea already. And later in the second part, then will be this, the second part will be dedicated to the main contribution. And I was saying before, I don't repeat these aspects of the disguise being a positive measure set, of the affine equivalence, so the preservation of the toric locus under invertible affine transformations, and later about the topological structure of the toric locus of a reaction network with the references I mentioned before. So I think it's a right moment to start making a quick introduction in the terminology of reaction networks. So in this context, we are working with chemical complexes. Let's say this says chemical, but it's not doesn't have to be really from chemistry in this sense. So what are complexes? They are formal linear combinations of species. We call them species. For instance, here we can look at this network. We have reactions. So we have 4 reactions. These are the edges, the directed edges, because we look at it as a directed graph. And the network is a directed graph. We consider in this example 3 species. Let's call them x1, x2, x3. And here then the complexes are labeling the vertices of the graph. So we have formal, as I said, formal linear combinations of the species, x1 plus x2 and so on. 2x2, x3. So this is a reaction network for us, a directed graph labeled, so whose vertices are labeled with these complexes that are formal linear combinations of the species. Okay, so why I want to specify also this, make this introduction is because we so some researchers consider working with reaction networks as embedded graphs. So not just abstract graphs, but let us place these graphs in the Euclidean plane, space. And in the sense, and that's why they are called the Euclidean embedded graphs, just because we prefer to look at them as, so the vertices, we see them as points in the Euclidean space. So for instance, how do we do this? For instance, this complex, x1 plus x2. So considering we have 3 species, as I was saying, so we are in the 3-dimensional Euclidean space, we can associate a vector y1, for instance, to in this case for the first vertex, given, so whose entries, the entries of the vector are the stoichiometric coefficients here in front of the species in the linear combination. So here you have 1 times x1, 1 times x2 in the second entry, and 0 times x3, so 1, 1, 0. And directly we place the dot according to this point in the Euclidean space. So y1 here in the picture in the right-hand side, y1, 1, 1, 0. You see is 1, 1, and 0. Similarly, for the second linear combination and for all the vertices, we get these points in the Euclidean space. And here it's 3-dimensional space. These kind of graphs are called Euclidean embedded graphs. And in some research works or books, you can see them abbreviated by E-graphs. So sometimes they're called E-graphs shortly. What are the advantages of working with E-graphs? We'll see, of course, during the tutorial in action how this works. Today, just the big idea, but essentially working with these graphs allows us to use geometry in order to understand the dynamical behavior. So the geometry of the network helps us understand the dynamics of the dynamical system coming from that network. And well, you can also, so of course, algebra, of course, comes also into play, because you can also think of this in terms of monomials, and we'll see soon what. But for now, let's think of this. And the second advantage of working with E-graphs is that reactions that were edges in the previously, I showed you that, so it was reactions were these edges, the blue edges, the blue arrows, now become, so reactions become vectors. They become, so the reactions become differences of the extremities of this arrow. So it's really a vector. Each reaction becomes a vector. So this is the second advantage. We will see how to use these vectors in that we will leverage them in our work. So let's go further. If there are questions, probably during the tutorial we can see more precise or more examples. But during the beginning of this talk, I mentioned that we work under the assumption of mass action kinetics. So it's a good moment to specify briefly what we mean by this. So essentially, we can, if we work under the assumption that the rate at which a reaction occurs is directly proportional to the product, so to the product of the concentrations. I'll make this more precise, but let's understand this. Is directly proportional to the product of the concentrations of the interacting species. This is how the rate of the reaction occurs. And we have, in this direct proportionality, we have this reaction rate constants that give the proportionality, and these are denoted by K, let's say Kij. If you go from vertex I to vertex J on your directed edge, that's the reaction. And these are positive real numbers. If you consider also 0, then essentially the reaction doesn't appear in the graph. So let's say they're positive real numbers, Kij. And you already see that some real algebraic geometry is coming into play already. So starting from now, at least. So the mass action kinetics is this assumption. We are working throughout the entire lectures. Now, what we want to do, essentially, when we work with these dynamical systems, we want to model the concentrations of the species in time. So how they behave in time, how they evolve, these concentrations of the species, how they evolve in time. So that's how we obtain polynomial ODE systems. Let's see how precisely we get this under the mass action kinetics assumption. So let's denote by small xi the concentration of the species xi, capital Xi. In this example, you have 3 species, so it's just simpler to see. And of course, this concentration is a function of time, depends on time that passes. So these are functions of time, and we want to see dxi over dt as we want to control this. If we write in a vectorial interpretation or notation, because it's more convenient, we can model the variation of the concentrations with time as follows. So we have d over dt of this vector with 3 entries, the 3 concentrations, functions of time. Okay, and let's see how to get the right-hand side of this polynomial ODE. So this is, was also already introduced by Beatrice, but maybe in a different manner. Of course, it's exactly the same. It is the same polynomial ODE system, but let me show how we prefer now to look at this. So I said that we have the rate that is given directly proportional to the product of the concentrations of the interacting species. So let's look at the first reaction. Let's say K1, this one that is the K12 that is labeled by K12. This arrow here on the left-hand side. And the interacting species here are x1 and x2. So we transform this into a monomial. See, we have now x1 times x2, okay, and the reaction rate is k12. So we have k12, x1, x2 times, and here we place the as I was saying previously, the reaction. Sorry, it's exactly this reaction. Let's see, so from 1 to 2, y1, y2. So it will be y2 minus y1, as I was saying. So 1, 2 minus y1 gives us minus 1, 1, 0. And here is the vector that we place. So minus 1, 1, 0 times, so again, this is a vectorial notation, times this monomial, where the k is a real positive number, and the monomial comes from, so the exponents actually of this monomial, you can look, it comes from these vertices, 1, 1, 0. That was the vertex of the network. So it's actually x to the power 1, x1 to the power 1, x2 to the power 1, and x3 to the power 0. And do the same for all the reactions in your network and sum them all up. You see here, for instance, 2x2 becomes x2 squared, as I was saying. We look at it in the monomial way. And since from 2x2 there are two reactions that emerge, we have x2 squared here appearing twice in two terms here. We can, of course, do this more generally and write it as in a more compact way, of course, following the same terminology. So let me give this definition, but it's exactly what I was saying here above, that the dynamical system generated by G, so G is our graph, the network, and K, so these are the parameters, Kij, that decorate our edges, so these are positive real numbers. How many of them? The number of edges in our graph, G. So the dynamical system generated by G and K is the following. In a vectorial way, dx over dt is this f that we use further on. So you should, so please keep in mind this notation, capital F, index G and K. So here G is fixed, the network. K, again, in this case, it's fixed. So we say that it's generated by G and K. And who is this F? Well, it's exactly what I was telling you. We take the sum over all the edges in your graph, take the rate that decorates that edge, multiply with the monomial. Here, X, of course, is a notation in multivariate abbreviation, and Y as well. So it's x to the power y. And as I was saying, x1, x2 here was x to the power 110. And you multiply with the difference of so the target and the sources, like target minus source of your reaction. This is a vector, as I was showing above. This is the way to model under mass action kinetics polynomial dynamical systems coming from reaction networks. And during the tutorial we can see more, but I think this is clear. If not, please let me know, and I can explain something if there is something unclear. Otherwise, I will pass to the next notion in this talk, which is actually the most important for now, because that's how we will end up understanding what is the toric locus, what are toric dynamical systems, because up until now there was just theory about reaction networks under mass action kinetics. So what I showed here is general theory for dynamical systems generated by a network and a set of parameters decorating the network. But now let's look at complex balanced or vertex balanced steady state. Now, first of all, what is a steady state? I'm sure you saw last lecture in Beatrice's talk. So just to say briefly, to recall, so a steady state is a zero solution of the right-hand side polynomials, because here there are three polynomials in this case, right? So we have three polynomials, we look at the common solutions, common roots, and we only care about positive real numbers. So that's something to keep in mind all the time. But sometimes in this, in several works or in some contexts, we approximate this by looking at the complex, all the complex solutions, and then intersect, of course, with the positive orthon. But sometimes we cannot do this. But in any case, by definition, a steady state is a positive real common solution of these right-hand side polynomials that appear here in the ODE system. Of course, because then the right-hand side is zero, and we have a steady state. It appears with some other terminologies sometimes, but we call it here steady state. I remind you that. Oh, okay, maybe I saw. So given we say that a steady state is vertex balanced, and you see this word already tells you, so vertex balance, you see why we call it like this. If for every vertex in your network, let's say briefly, what goes in that vertex is balanced with what goes out of it. So the flux into the vertex is equal to the flux out of the vertex. And soon I'll explain what I mean. But essentially, you can consider similarly to Kirchhoff's junction rule in electrical networks. So, and here, let's take each of these vertices. Here we have three vertices to see precisely what I mean. So consider this first one, for instance. What goes out of it? How we consider the fluxes, because I didn't define them, but the fluxes. So out of it is K12 times X1, X2. Here I added these hats because we are talking about the steady state of the system, so fixes steady state. So this is the right-hand side, and what goes inside that vertex, this is K21 times the source here, so X2 squared. Again, we think in terms of monomials in X, plus K31, so we have this other edge. I hope you see the mouse. I hope you can see my mouse. I'm sure.
Yeah, we can see.
Thank you very much. So the second reaction is K31, and you add here this term K31 times its source, that is X3 hat. Again, it's the monomial here is very easy. So you add all the influxes and you balance out, you say either equal to the outfluxes for that vertex. So this is very important, and we will see this during the tutorial, because here that's first step to compute the toric locus. So this is the first step where, so when you can start the computation of the toric locus by imposing these vertex balanced equations that I want to mention. These are also called complex balanced, but not. I received this question at some point. Someone was thinking that complex balance because we work under the complex numbers. There's that's not the reason, but because as I was introducing the definition, it was about complexes, species, and so on. Complex balance, we balance out each complex. In other words, we balance out each vertex in this network. And similarly, we get for each vertex such an equality. So you see here is again where real algebraic geometry comes into play, because we get equality, we get polynomial equalities, systems of polynomial equalities, nonlinear. They're nonlinear in X. They are linear in K. In the beginning, I was saying that some nonlinear algebra, some linear algebra, they're very useful, both of them, in this subject. So let's look again at these equations, polynomial equations, with coefficients in positive real numbers. The coefficients are Kij, the K's. Sometimes I call them coefficients, and sometimes I call them parameters. That's the parameter set that I will talk about, that I was talking before. So please keep in mind, these are the parameters, Kij actually. But let's see. So we look at these equations first. There are two ways to look at these. First way is for fixed Kij, so for fixed rate constants, Kij, or they're also called, as I said, coefficients, parameters. Sometimes we interchange these. For fixed Kij, so for fixed vector K, you would like to find maybe X. That's one way to look at this system of polynomial equations, but we won't do this. We actually look in a second way, namely, we consider, and here I would like you to think of the elimination theory. That's why I really wanted to make a lecture about elimination theory. We can think, for which K does there exist an X satisfying such system of polynomial equations? So here is exactly what we were seeing last lecture with elimination theory, and I was mentioning in terms of quantifier elimination also. So for which X do there exist, for which K, excuse me, for which K do there exist X's that satisfy a system of equations? So finally, here we are ready to understand the definition of the toric locus. Finally, I couldn't say it before, it was a bit technical in the first slides, but namely, the toric locus is the set of positive real numbers Kj in the parameter space. So, okay, you can think of this as a vector of Kij in the parameter space, okay, such that there exists such a vertex balance solution X hat. So this is the toric locus, and I guess you already realized or grasped the fact that you can use elimination theory here and elimination ideals, and there is a lot to say, but in the next lectures, maybe the idea is that real algebraic geometry in the terms of real quantifier elimination, or commutative algebra in terms of elimination ideals and so on, is very useful in determining this toric locus. And now, okay, you might wonder, why do we want to find the toric locus? Why? I said in the beginning a bit that it's very nice from the dynamics point of view, but didn't make it precise. And now I would like to do this. So I gave this list of references in the beginning about the fundamental work of Horn and Jackson in 1972. And this is this is the main reason why we care, and the community in reaction networks cares about toric dynamical systems. So this is the reason. The reason is that they are very nice from the dynamical side, and rigorously stated, the theorem is the following. So let's say we have a mass action system. So as I said, okay, those polynomial ODEs. If a mass action system has a vertex balance steady state, if it has one x star here, that is vertex balance, so that satisfies those equations of the Kirchhoff equations, let's say. Then, first thing is that all positive steady states are vertex balanced. Moreover, there is exactly one steady state up to conservation laws. So up to this stoichiometric compatibility class that gives you the conservation laws, and so in this invariant polynomial, we'll see a bit more precisely, but up to conservation laws, there is exactly one steady state. And I jump to the third point now. What is very nice about this steady state is that, or like about all the positive steady states, that they are locally asymptotically stable up to conservation law. So if it has one vertex balanced steady state, if the system has one vertex balanced steady state, we know that all the positive steady states are vertex balanced, that there is exactly one for each, so up to conservation laws, but moreover, not only that there is exactly one, but they are locally asymptotically stable. This is proven to be, they are proven, we know that they are locally asymptotically stable. And okay, we also can think of this in terms of Lyapunov functions, and maybe for now I don't mention too much, but we even have a strictly convex Lyapunov function. I mean, Horn and Jackson provided this function that has a global minimum at this vertex balanced steady state X star. So that's great. And this is the theorem that I was mentioning in the beginning, that the fact that the toric dynamical systems, or that are also called vertex balanced dynamical systems or complex balanced dynamical systems, are extremely nice from the dynamical point of view. Extremely nice. Proven to be extremely nice by Horn and Jackson. So there's a lot to say. There's even, I recommend here also a book that I didn't write in the references by Feinberg, Chemical Reaction Network Theory, I think. I can, if someone, please remind me if you, I might edit it during the tutorial. And their ideas are inspired by thermodynamics, and there's a bidirection, okay, so there's an interplay between thermodynamics and chemical reaction network theory, because they ideas from thermodynamics inspired chemical reaction networks, like in this example, but it goes also the other way around, and yes, that's the key point. Now, sometimes I was mentioning also global stability, and that's the point where I should mention that there is this conjecture that vertex balanced equilibria are globally asymptotically stable, not only locally asymptotically stable. There's a conjecture, there's a story about this conjecture, and you can read more about this in this review paper by Yu and Crăciun that I mentioned in the beginning. You can see in which cases this has been proven, and where is still open and why, and other details about it. But in many cases, under mild hypothesis, this has been proven. So in many cases, we know that they are globally asymptotically stable, these vertex balanced steady states. Very, very, very nice dynamics. It's desirable for applications. Here I was mentioning this global attractor conjecture. What does it say? That I say more in detail. It says that toric dynamical systems are globally stable within each positive stoichiometric compatibility class. So that means they have a globally attracting point up to conservation laws. This is the reason why toric dynamical systems are very interesting for us. And as I said, it's proven under mild hypothesis, and a recently proposed proof in all generality is given by Crăciun in this preprint here that I added the URL archive to it as a footnote. Okay, So maybe I think I have 8 more minutes, or could you please confirm?
Yeah. Just 4 minutes or 3 minutes if you would like to stop, so we can utilize that time for the question and answer.
Oh, okay. I'll do my best. Okay. This was in any case intended for these slides were intended for probably 2 lectures, because there are many examples to talk about. But let me just finish with because I said here I want to make more precise the dynamics, and I did this. And now to make more precise also a bit of the algebra, and next time we'll see more proofs and so. But I wanted to give the big idea. First, there is a theorem from Karin Gatterman in 2001, saying that the steady state set, so the set of all steady states, that is one for each stoichiometric compatibility class. So we just get the steady state set. So this set for a toric dynamical system is a toric variety. So you can use monomial parameterization, and there's a lot of there are plenty of works about this as far as I know. But now we won't look at these results in these lectures, but I still wanted to specify this. What we look at is the following theorem, that is the starting point for us. A theorem by Crăciun, Dickenstein, Shu, and Sturmfels in 2009, that says that the moduli space, so the parameter set in the parameter set space, the parameters that give rise to toric dynamical systems, is a toric variety. I didn't mention before, but after a change of coordinates. So we need to make a change of coordinates, but that's very nice. And in terms of the matrix tree theorem, we'll see another time. But the idea is that these are the 2 reasons, at least 2 reasons for which these systems have been called toric dynamical systems in 2009. And maybe I show you this example just for this theorem, the second theorem. If, for instance, we look at this reaction network, it has 3 vertices and edges we have that are directed edges. It's complete directed graph on 3 nodes. The moduli space associated to this network is given by this equation, algebraic equation. So it is a hypersurface in the parameter space, a 6-dimensional parameter space, because there are 6 edges of the graph. And if you know now that, and with this I will finish now, you know that if you take parameters on that hypersurface, on this one, so that they satisfy this equation, algebraic equation, the system coming from those parameters is toric, so has those nice dynamics. So it's a nice way to see. But again, it's a hypersurface. So in this case, you see that this is the disadvantage, that it's a Lebesgue measure 0 in the parameter space. So quite rare. And just to conclude, of course, here you don't see so maybe not the first sight, you don't see, but if you look at these parentheses, maybe you notice that after a change of variables, you get a binomial equation. And that's where the toric comes into play. Okay, so yes, I can stop now, and I will continue next time.
Thank you, Miruna. Are there some questions from the audience side? Yeah. Maybe he's the first. Okay, sorry.
Lyapunov functions are very useful in the dynamic systems. My question is that which journal met for that help us to construct the Lyapunov functions?
The question is which journal, or sorry?
Journal formula or methodology to construct the Lyapunov function?
Lyapunov. So,
from here,
Lyapunov.
Second point.
yes. So I recommend the details are here, all the details in this because it's more involved here, but it's a precise function. I can give you next time the function, and there is very much described in the book by Feinberg and in this paper. But for now. That's what I wanted to say. Only this in this. I was planning to mention this during the tutorial
Okay.
to gain time. But this is we have the function, and that's nice. But precisely because of this function and its level sets, we have only a conjecture that this is globally asymptotically stable because the level sets of this function might intersect the axis, the coordinate axis, and then in that situation precisely, we don't know, we don't have a proof. I mean, they don't have Horner and Jackson don't have a proof because initially they believed that this function gives the proof for globally asymptotically stable, and only afterwards in a second paper they came back and said, okay, this is actually not always true. We only have local stability because of the level curves of that Lyapunov function might intersect the axis, and in that case the trajectories could go to those intersection points and might not go to the global minimum x star. Some trajectories might end up on the intersection of the level curves of the Lyapunov function with the axis, with the coordinate axis. Maybe next time I plan to add a picture with this situation.
Miruna, there is another question.
Yeah, can I ask you a question? So,
Yeah.
hello.
Go ahead.
So, the after the change of coordinate, the last slide in the section, the variety, toric variety in the real case is going to be a kind of cone, right? It has a similarity. The last one, the next one. Yeah, this one. If you reparameterize this one, change the coordinates, right?
So we think of this now in an affine setting.
Okay.
So
this is this is the equation of a cone, right? It's like xy minus d square equals 0.
We think of this finely, but once you make the change of coordinates, indeed you get such equation. And in these new coordinates, you can think as you wish. But for now, I am really thinking here that we are in a fine 6-dimensional positive orthont. And if you want, you can also. So in next time, I will talk about these things more, like the variety, the toric locus, how you get it, and what. It was not intended here in this lecture. Here we just, I wanted just to see them as parameters and finally here, but yes, next time that's the goal, to look at this variety, to prove why it is toric variety, and how to get it using some elimination ideals and so on. So I would leave this to the next, if you have some patience, we will get there.
Okay, so then no problem. Then it's the question for the next lecture. Okay.
But thank you very much for the questions. I'm happy to have questions.
Yeah, Sam.
Yeah, I was just wondering about the vertex balanced. It's a little hard to exactly see how a steady state is not vertex balanced for me. Do you, if there's not a simple example, maybe we can have an example later?
Oh, thank you for the thing, so that I know how to, for suggesting this, I will prepare. But essentially, here, so here is where the elimination comes into play. I think this is your question. So you asked me where when a steady state is not vertex balanced, right? Yeah.
That's
Did you
correct,
ask
yeah.
me? And I was saying that is vertex balanced when so X hat verifies such a system, and here I was saying that we are interested in the set of parameters K when there exists such an X hat. So exactly this is the I thank you for asking me this, because this is the whole point for the toric locus, namely. So we know that if the parameters are on the toric locus, for sure there exists such an X hat. But also an important thing is that that's all. I mean, I'm not saying that if a parameter is not on the toric locus, so to say, if it's not on the toric locus, we don't know. And that's precisely where our work comes into play, because we extend the toric locus with some more parameters, where we will also know that if you pick from the extended, so from the disguised toric locus, the bigger one, if you pick parameters vector from there, you also get such a nice solution. So how do we know? How do we know? Is by plugging in exactly these. Sorry. So here, if you plug in, then you know for sure it's. And there are, and also there are. I have examples. Yes, where I will show examples where. So there are some combinatorial properties on the graph when we know that yes, that there is no the toric locus is empty and so on. But even if the toric locus is empty, again, that's the point. We can extend it to some bigger set that's not empty, and where we know that there is a solution X hat that is vertex balanced. So maybe next time with some more examples we can see. But here is exactly where the elimination that I showed in the first lecture comes into play, because you plug these equations in your ideal, and you eliminate x1, x2, x3, and you get, if you try, you can try this at home. You get exactly this this polynomial equation in Kij, because you eliminate all the x's and you get all the parameters Kij for which there exists an x. So please keep in mind always this connection with the elimination ideal that I showed in Macaulay too in the first lecture.
Okay, Miruna, one question which simply arises from all these questions. So particularly, this particular work is a kind of the translating all the dynamical system parameter things into the dictionary of algebraic geometry and dealing them from the algebraic perspective, just like the Lyapunov function, and then you are using the Kirchhoff condition in order to construct a toric variety. And are you going back from algebra to dynamical system as well?
Yeah, yes. So in some sense, there is a translation, but maybe I'm not sure if directly from the Lyapunov to this, the Lyapunov and the theorem by Horn and Jackson is mostly for us. It's a motivation to study these systems, at least how I see it now. But yes, it is going also backwards, and that's the whole point, because what we do is exactly in this example, for instance, we have the algebraic condition, and also geometry, because there's this variety and so on, where you can pick points and so on, that ensures that you have this nice dynamics. So you go back to the dynamics. But this condition ensures that you will have that dynamics because of the Horn and Jackson theorem, saying that if it's vertex balanced, you have that nice dynamics. And the vertex balance indeed is actually the vertex balance by definition is algebraic because you balance out the left and right, the influx and the outflux. So it is an interplay. It is really an interplay between the dynamics, the algebra and geometry, computations, and combinatorics. The next time I will show you a lot how, and maybe I'll not go into details, but I'll show you how the combinatorics of the graph and the Euclidean embedded graphs and this geometric point of view helps us extend the toric locus to the disguised toric locus. So the parameter space that you're sure gives the nice dynamics to a bigger parameter space where you will be sure you will have the nice dynamics.
I was just curious about that particular reference which you mentioned, which was stating about the Hilbert 13 problem. That is the problem which is related to the stability of the dynamical system.
Sorry, the reference, which one?
Hilbert 13, I think problem.
Ah.
Can you go to the references? Yeah, it's the one.
Yes.
Yeah, Hilbert 16 problem. So
Yes.
are they going to address the stability problem of the dynamical system, which is, I think this problem is related to the stability of the dynamical system.
It is definitely. So we know, so thank you for the question. First of all, this is a motivation, the Hilbert 16. We won't work about Hilbert 16, but I thought it's nice to edit here. Maybe I could have also added as an example Lotka-Volterra in the for the context, but we don't work precisely with this Hilbert 16 problem. However, yes, the stability plays the most important role. Just let me maybe not just a second to see where we sorry for skipping, but I want to here. So we know that these systems that are called toric dynamical systems that appear in the literature also as complex balanced dynamical system, a lot complex balanced dynamical systems or vertex balanced dynamical systems, we know they are locally stable. So it was proven, this was already. So I won't, unless you would like to talk more about this, I won't use more this. I just, we know from Horn and Jackson they are stable, locally stable, and in some settings, globally also globally stable. So that's very nice.
Okay, thank
In
you.
some settings it's proven, and in other cases it's still just a conjecture with a proposed proof. And I showed you that reference in the slide where we know that it's also globally. So we don't, now we know this, and we are wondering which is the parameter space that gives you this local stability and global stability. That's the goal.
Thank you very much. If there are no more questions, so then let's thank Miruna. Thank you very much.
Thank you very much.
And okay, after this, now there is a tea break, and after the tea break, there will be a discussion session, general discussion session on the problem. What Sarah keywords.